My dear student, today we'll be discussing some properties of Lebesgue integration of real valued function. So we are going to extend those properties of non-negative measurable functions to the real valued measurable functions. So it is not new, but the thing is that earlier the function is non-negative and now it is a real valued measurable function. Okay, so yeah, first let us define the integration of a function over a set E. So suppose A is a measurable set and f is a measurable function, and then we are assuming that chi e f is also integrable. This function is integrable, chi e f is integrable, and then we say that f is integrable over the set E, and its integral value, its integration is given by this. Now f dx over the set E is equal to integration of the function f chi e dx. So here the integration is all domain, the set of real number R. So here the integration is over the domain, E. But we are putting here chi e, so this equality, and this is called the integration of the function over the set E. So this is the new definition. Then if a function is integrable over a set E, then we use this notation. Okay, f belongs to LE, so means LE means the set of all Lebesgue integrable function over the set E. So this is the definition. Okay, and next let us extend those results we prove in non-negative measurable function. So here f and g, okay, so are integrable functions. So integrable function means, in the last class we defined what do we mean by an integrable function. So then we are going to prove that a times f, where a is a real number, is integrable and its value is equal to a times integration f dx. Okay, so similarly, if f is integrable and g is integrable, then f plus g is integrable. Its value is given by integration f plus g dx is equal to sum of the integration of f and g. Okay, so and next, if f is equal to 0 almost everywhere, then the integration of f dx is also 0. This is 0 value. This also we did for non-negative measurable function. Now we are going to extend that to a real valued measurable function, and if f is dominated by g, that is g is greater than or equal to f almost everywhere, then integration of f is less than equal to integration of g. So this also we did in non-negative measurable function. And lastly, if a and b are disjoint measurable set, then this is equal to, that means integration over set A union B for the function f is equal to integration of f over the set A plus integration of f over the set V. So these 5 results we are going to prove, and this is the extension of the result we prove in non-negative measurable functions. Okay, first let us prove number 1. What is number 1? Integration, if f is integrable, af is integrable, and its integral value is given by a times integration of f. So this is the one we are going to prove first. First let us suppose that a is greater than or equal to 0, means a is non-negative. For non-negative case, let us prove it first. Then f is a function, af is another function. Its positive part is equal to, by definition, af 0, or maximum of af 0. Alright, then since a is positive, you can take out this a outside the maximum function because a is positive. Okay, so then it is equal to a times positive part of the function f. And similarly, AF negative is equal to maximum of A minus F 0. Again, since A is positive, you can take out A outside the maximum function. So this is equal to A times negative part of the function F. So because of this result, what you have now here, the positive part is non-negative real valued function, measurable function, and this F negative, it is also non-negative measurable function. So those result is true, we prove in the non-negative case. So then AF integration of AF positive part is equal to A times F positive. Okay, so now this is a non-negative real valued function. Non-negative real valued function. For the non-negative real valued function, this constant can be taken out outside the integration. That is why you are getting this one. Okay, but since F is integrable, integration F positive dx is finite. So this finite quantity is multiplied by another finite real number A, then it is finite. Okay, this is positive, this is positive, it is finite. All right, so similarly, you know, A times AF negative part is equal to A times negative part of the function F, but this is non-negative real valued function. So for this one, this constant which is non-negative can be taken out of the integration. That is why you are getting this one. But again, it is given that F is integrable. That means integration of the negative part is finite. So multiplied by another finite real number, non-negative, it is less than infinity. Okay, so what does it say? It says that this is okay, this is finite. Ultimately this integration is finite, this integration is finite. So from the definition, integration of this function AF is equal to the positive part plus this positive part, integration positive part, this one, minus integration of the negative part. This is the equality from the definition. All right, so again you can take out A outside the integration because this is non-negative real part, non-negative part of the function. This is also, this is also non-negative function. Therefore you can take out A outside the integration, so you will get this one. But this one is nothing but the integration of F dx. So ultimately what you get, integration of A times F is equal to A times integration of F dx whenever A is a positive real number. This is done for the case of positive real number. We have done this one, and suppose let us assume that A is minus 1. When it is minus 1, what happened? AF positive part is equal to minus F positive part is equal to, by definition, maximum of minus F is equal to 0, but maximum of minus F is equal to 0. This one is equal to negative part of the function F. So similarly, AF negative part, this is equal to, so minus F negative part, this is equal to maximum of minus F. This is maximum of F. This is equal to F positive. So this is equal to F positive and this is equal to F negative. This is very straightforward. Okay, so then what happened? Integration AF positive part, this is exactly equal to F negative dx, but since function F is integrable, this quantity, this is finite. Okay, so similarly AF negative dx, this is equal to F positive dx, and this is finite. All right, so what is integration AF from the definition? This is equal to integration of the positive part minus integration of the negative part, but the positive part here is F negative because A is negative, minus 1, and this you have got this one. Okay, so that means what? If you take minus 1 common, then you will get this one. But what is this? This is integration of F dx. This is equal to minus time integration of F dx. What is minus 1? Minus 1 is your A, so you get this one. All right, AF dx is equal to A times integration F dx, and whenever A is equal to minus 1, that is, in another language you can write this one, minus of F dx is equal to minus integration F dx. Okay, so the result is proof when A is equal to minus 1. Suppose if A is not equal to minus 1, say for example A is equal to minus 5, then what happened? Let us see. A times F is equal to, so minus modulus a f, this equality is true. But if you put a modulus a times f is equal to another function g, and then you can write in this form where g is equal to modulus a times f. Okay, so this is the equality you have. So since f is measurable, then the function f multiplied by another real number, that is g, is also measurable. All right, so what is af dx? So af dx is equal to, according to the new definition of the function g, it is equal to minus modulus a f dx, but modulus a f is equal to g, so it is equal to minus g dx. So but by the case number, by the above case, that is when a is equal to minus 1, by this one that just now we have done, integration of minus f dx is equal to minus integration f dx. Because of this one, what do you get? So minus 1 you can take out side. Okay, this is the one you get it. All right, so again, what is this? This is equal to minus modulus of a times f dx, but modulus of a is positive number. For the positive case we have done, so this positive number can be taken out of the integration just in the above case. So this minus of modulus a is equal to simply a. All right, so ultimately what you get, whenever a is non-negative, the a is not equal to minus 1. So whenever a is negative and a is not equal to minus 1, a times f dx is equal to a times integration f dx. All right, so this is the one, Roman number 2 we have done. Roman number 2, for the first one we have done. Let us now prove Roman number 2. Roman number 2. So again, a positive part of f plus g is equal to, by definition, maximum of f plus g, and this is, less than equal to maximum of f0 plus maximum of g0. So this is obvious, that is what, but this is one equal to f positive and this one is equal to g positive. All right, so this, let me explain how it comes. Suppose f is equal to, 5 and g is equal to minus 2. Then what is f positive? F positive is equal to maximum of 5 and 0. This is equal to 5. Right? What about g positive? G positive is equal to maximum of minus 2 and 0. This is equal to 0. All right, so what about f plus g? What is f plus g? Is equal to 5 minus 2 is equal to 3. So then what is the maximum of f plus g? This is equal to, so maximum of 3 and 0, this is equal to 3. So that means what? It is obvious from this. So maximum of f plus g, this is less than equal to maximum of f, that is 5, maximum of g, that is 0. All right, so 3 is less than equal to 5. Okay, so this is true, that is, in some case it equality holds. So yeah, so maximum of f plus g is less than equal to maximum of f plus maximum of g0. Okay, so that is equal to f plus plus g plus. All right, so that is what this equality always true. Similarly, for the case of negative, this is also always true. Okay, so that means what? This is non-negative measurable function, so Lebesgue integration is defined. This is also non-negative measurable function, so it is also a Lebesgue integration is well defined. So again, from that property, integration of this one is less than equal to integration of this one. So integration of this one is less than equal to integration of this one. Again, by that property, since it is non-negative measurable function, so that integration of f plus integration of g plus, this is equal to what? Integration of f plus plus integration of g plus. So both are finite, that means their sum is also finite. Similarly, this is less than equal to this one. All right, so that means what? Since they are finite, their sum is also finite. Okay, that means what? This integration is finite, this integration is finite, therefore integration of this function is defined, well defined. Okay, so but this function is what? It is equal to positive part minus negative part. This is equal to, from this what do you get? This f is equal to f positive minus f negative, but this g is equal to g positive minus g negative. So from here you write positive part and then negative part like this. Okay, so by transferring this, you transfer this side, and this side, you get this equality. So these are all non-negative real valued function. All right, f plus g positive is a non-negative real valued function. F negative is also non-negative real valued function. G negative is also non-negative real valued function. So this term also all non-negative real valued function. Okay, so for this one we have already done the theory. So that means integration of this equal to the integration of this one, but integration of this one can be broken down like this one: integration of f plus g positive part plus integration of f negative part plus integration of g negative part. This is because why? All the function here, they are non-negative real valued function. So similarly this part you can broken down like this. All right, so then you interchange, you write this one, and then you transfer this to this side, you get this one. Then you write this first, then this is coming from left hand side, then you get this one, you get. So look at this expression. This is what? This we have just shown that this is finite and this is finite. If this is finite and this is finite, this difference is called just integration of f plus g. Okay, so this is equal to integration of f plus g. All right, so similarly, since f is integrable means this expression is exactly equal to this one. Similarly, this one is exactly equal to this one. Okay, so ultimately you get this one: integration of the function f plus g is equal to integration of the function f plus integration of the function g. Okay, so we have done Roman number 2, we have proof. And next, Roman number 3, let us see what does Roman number 3 says. So Roman number 3 says that if f is equal to 0 almost everywhere, then integration of f dx is equal to 0. So for this one we have done for non-negative real valued function. Okay, so f positive is what? F positive is equal to maximum of f and 0. Similarly, f negative from the definition is equal to maximum of minus f0. From this definition, it is straightforward that if f is equal to 0 almost everywhere, then f positive is also 0 almost everywhere. Okay, similarly f negative is also 0 almost everywhere. This is very straightforward. Okay, so if f is 0, f equal to 0 almost everywhere, then f positive is equal to 0 almost everywhere, f negative is also 0 almost everywhere. All right, so then we have done one example that if a non-negative function is 0 almost everywhere, then its integration is 0. Therefore integration of f positive is equal to 0, integration of f negative is also 0. So they are finite. 0 means they are finite, so their difference will be the integration of f. So that is 0 minus 0, that is integration of f is equal to 0. All right, so whenever f is equal to 0 almost everywhere, its integration is equal to 0. Okay, so next let us prove this one. Suppose g is dominating f almost everywhere. All right, so again this one, from the definition, it is almost obvious that g minus f negative part is equal to maximum of f, f minus g. The negative part means you have to multiply by minus, so after multiplication you get f minus g, 0. All right, so if g is greater than f almost everywhere, then maximum of f minus g, 0 is equal to 0 almost everywhere, because if g is greater than f or f almost everywhere, then f minus g is equal to 0 almost everywhere. If this function is equal to almost everywhere, then the maximum function is equal to 0 almost everywhere. All right, so then by result 3 we are going to apply result 3. If g of g minus f negative part is equal to almost everywhere, then its integration is equal to 0. All right, but you can write g in this form: g is equal to f plus g minus f. So by Roman number 2, what do you have? You are having two functions and their sum. The function f is integrable, the function g minus f, this is also integrable, then their integration is equal to, you know, that equality, okay, sum of the integral. So then f, you know, this is equal to what? Integration g dx, then integration of f dx plus what is the integration of this one? This integration of this one is integration of the positive part minus integration of the negative part. This is the integration of the positive part and this is the integration of the negative part, okay. But since g minus f negative part is equal to 0 almost everywhere, its integration is 0. Just now we have done this in Roman number 3. So this part is 0. So this is non-negative function, its integration is not 0 or not negative, okay. So this, so ultimately what you get, this integration is equal to this plus some non-negative term, okay. So that means this is greater than this one, huh? Because you are getting this one after adding some non-negative number to this f, okay. So therefore integration of g is greater than or equal to integration of f. This is obvious. So we have done Roman number 4 also. Now let us prove the last one. This is very straightforward. So for the characteristic function, if a and b are disjoint measurable set, characteristic function a union b is equal to characteristic function a plus characteristic function b. So this is obvious, we have done this one earlier. Then if you multiply by function f, you get this equality, then you get integration, okay, integration of this one a union b integration f dx. Integration of this one is equal to f over the set a union b, okay. Similarly, just now we have done, this is a function, this is a function, so their integration is equal to integration of this function plus integration of this function, okay. But integration of this function is what? That is from the definition, integration of the function f over the set a, okay. So integration of the function, this one is what? Integration of the function f over the set b. So Roman number 5 we have done. So this completes the proof, okay. So this looks very simple, but it is very powerful and very useful also. Later on we are going to use this theorem again and again, and everything will be simplified for our, you know, integration. All right, so this much I want to give you today. Again, this is the beginning, okay. So you give some emphasis to learn this one. All right, so let me stop here.